Hi everyone. So I'm here to present you the first project. Loops are given. To remind you the subject of this project, the goal, the challenge was to develop an algorithm to add a 6 loop without loop. It's as many as low as we can. So this is what we try to do in this project, and we will present you about the step by step. So how is that? Or you start with the first slide?
So first we went to, because there are a lot of optimizing tools in Python and so on. So there are the 3 main ones, Numpy, Cython, we use C code basically, try to see, Pythonize your Numpy code, and then Numpy. So super acceleration code. Depends. So we tested those on the like 2 simple, like a 2 loop, the topic is so to make the distance a simple operation. And you have to loop it as a 2D matrix, so you have to loop through all those single points. You can also write it below as a single one line, basically, using Numpy broadcasting. And so now, just these 2 alone, these are like put in Numpy. So now we can also, let's say, Cythonize them, we just wrap it around, and so that it's defined as it would be in C. It's a little bit more maybe complicated, but since it's the same structure. Or you can use a number, and then it's super simple, just add this little 4 letters at the beginning of your function. Then you can test for those 3 possible initial optimization techniques how actually do they differ in terms of time of computing those operations. And so what you see, okay, the simple Numpy loop takes the longest, as what we call this factor. But there's a couple of things that are interesting. The first one is that if you write your code, if you Cythonize your code, you have, if you keep the loop, it's faster than if you use the broadcasting, because Cythonizing it will more operation. And on the other hand, if you use Numpy for these very simple cases, then it's keeping the loops is extremely fast compared to pure Numpy. So in this case, at least it seems that numbers essentially the way to go. Just do that. You keep the loop and so on. It's okay, fine. But well, I think now we will have a more interesting view on what you can actually do with the code.
Yeah. So just the basic idea: imagine you have an image. The problem has us to identify these patches. We're trying to identify all the patches around that patch. And that's all the information we need to compute the value for 1 pixel. So those are the 2 sets of loops. And the first thing we did one of the things we did to identify and simplify one of those pairs of loops was working on this function, basically defining the size of the loop patch. And adapting, creating this view that modifies the shape arc for the given array. So this is really not creating a new array. It's just creating a new view on the array. And our goal is to get all those 9 sets of patches. So to give an example. With that operation, we actually create a view that looks like a 4-dimensional array rather than a 2-dimensional your image. And what it's actually giving you is a way to index the patches directly. And every time you index a patch, you get all 9 numbers related to that patch. So the idea was to that basically gets rid of 2 for loops, right? The 2 linear loops. And we can now start thinking more abstractly, how can we move forward and expand this abstraction to be able to capture or index the set of patches directly. So going back to the original image, now we have this notion of patch sets that we want to extract for each pixel. So we're scanning, that's the outer two loops, scanning each pixel, and trying to extract for each pixel the entirety of the 9 patches being received. And so, going back to that function, the trick here was basically to expand the abstraction to include a notion of how many patches around the center patch do we want. And that's what we did here. It's an additional parameter. And to give you an idea, this is basically creating a view into the same array that now has a way to index the patch set directly. So with one, when we ask for one of these patches, we get all 9 of them, and then we can start operating directly on those matrices. And then it gets rid of another 2 loops. And those are the big examples. I'm going to show you. So this is how we solve the problem. The last part.
So after this second day, we were really motivated, and when we look at the original function, as you can see here, so this is the original function on your right, and as you can see, you have really long function with all the loops. Okay, it's really small. Really big, there is a 6 loop here, and it's really complicated to go through the code. And after that, this is our function. As you can see, we can do exactly the same thing with only one loop, the loop that you see here. So here we are iterating over each pixel of our array, okay? And the magic is here, the only set that or just explaining to you that's giving for each pixel the neighborhood or the different patch. So with that we can do all the computation, and that's done. We test it and we get exactly the same result as the code you see on your right, coming from a scikit image package. So after that, what was our feeling? Our feeling was a little bit of course, it was really great to see that we can succeed this thing. It's good to have this feeling, but is it beautiful? I mean, most of the people just don't care. The real question is it fast? So we look at that, and this is what we get. So we saw that our implementation in pure Python, it's only in Python, is really faster. It's 4, 5, 6 times to the Numpy loops or the Numpy loops. Okay. The original scikit image, as you can see here, is really fast. But the only reason it's so fast is because they approximate the exponential function in C. So since we are calling 10,000 times the exponential, for sure we are really slow. And the Python local.
Yes, the one with the Numpy explanation, not the C.
Yeah. So this is we copy the scikit image algorithm and we replace the exponential with the exponential that we had, and you can see how much it could increase the speed. So we are 4 times slower, but don't forget that they are in C and we are in Python. So what do we learn? So we learned that during this 3 days we learned a lot about forecasting, memory use, right, in Python. So Numpy is really awesome. I advise you to go deeper on that. You can do crazy stuff. We learned that Python implementation is you have to avoid the loops as much as possible because it's really slow. If you still want to use the loops, try to do it in Python. This can make your code faster, but you need the expertise. Also, as if you really insist and you want the loop, you can still use Numpy, but you have to create a really small function that can be tuned, that can be Numpy to accelerate them. And the bigger things we learn is significant. So try to simplify your algorithm. It was really, really, really complicated. So the future work, maybe. So maybe to extend it 3D, but it's not a lot of work. It's only one line of code. Synchronize the explanation, like I told you, and then yeah, that's all. So thank you all. Thank you all for this week. It was really good. Thank you to the speaker. If you have any questions, thank you for.
Hello, everyone. Okay, so in our group, we're really interested in understanding how mixed models can run an fMRI with fMRI data. So typically, when you're running an imaging study, you have behavioral data, and oftentimes the behavioral data is run with things like Elmer and R, but the imaging portion isn't. And so we kind of wanted to see what happens when we do it that way. And also, there's a lot of really great open longitudinal data sets, and analyzing longitudinal data can be really complicated, but less complicated with mixed models. So we were playing with the Neuropointillist package that we learned about in the lectures, and when we started going through them, we had some difficulties just kind of getting through the basic tutorials. So what we first did was we sort of expanded upon the tutorials and made our own. So we made 4 separate tutorials with a lot more details that broke down what each thing meant and what to do. And so that's an example of one of them. And then there's an argument file that they have in the model, and we sort of went through in more detail what each argument means. And yeah, that's just the good part.
There was one part of the code that required FSL maps. Like the whole thing is run mostly through R, but it has some bash scripts. And then there was this one little bit of required FSL maps, and to run just this one little thing, you have to download like, I don't know, 16 gigabyte. So we learned some other kinds of scripting. So we were able to change this one function to detect whether or not you have FSL on your computer. If not, when you don't have FSL, you use NiLearn. So we did some of that to our first Python code. Gong.
Oh, okay, yeah. So this is just breaking down the model scripts. Yeah, we sort of went through the script sheet before. This is another tutorial, but in the top of the model, if you specify the model like you would with an LME4 or a LME model, and then the bottom sort of gives you the T-stats and P-stats and all that sort of, and the contrast that you want to set up.
So the last piece of the original Neuropointillist tutorial looks like this. So they have an example using data that is only available to people at debug, and then the instructions are you can just look at the scripts and maybe learn something from that. So we wanted to make a version of this tutorial using data that was open for everyone, so people who actually wanted the tutorial on the web. So Chris told us about this data set that he has that's up on OpenNeuro. There's a version of the process. It's 10 subjects, each with a test and a retest doing some basic motor and language tasks. And so using that, we built the tutorial using open data. So instructions on how to download it, how to sort it, et cetera. And from there, we also realized we wrote another new little piece of code. Neuropointillist takes a mask and only runs the mixed models inside the mask of brain shape. We wrote a little piece of code to make a common mask since every individual person will have slightly different brain sizes. Another fun thing I ran into when testing our tutorial was a bug that was found in the code. I didn't realize someone else had found it before I did, so it took me a while to work through it. And that inspired me to get some help from Tal, making a piece of code to make a smaller mask that looks like this. So So if you run the code on the whole data set, when I was playing around with it, one of them took about 15 minutes to run, and then at the very end, when it tries to write out, it throws error, and then you want to smash your computer to pieces. So in this case, you can only run the code on this one slice of brain. It only takes maybe a couple of minutes, and then you're less frustrated and it does work. So we've added that to the package for troubleshooting as well. And then the last useful little bit of stuff that we did that we showed you is some very basic model comparisons. So again, this is from Chris's data set. We chose to use the word production task from the data set for no other reason than that was the one with the fewest number of TRs, so we thought it would run the fastest. And we only pulled 4 out of the 10 subjects, so each one is 15 time points. And these are the slides that were in our tutorial. So here's our first fixed text model, very basic. What does the brain activity look like as a function of whether or not they're doing this word production task? And because it's only 4 subjects, very low, or I see right here, very low thresholded, but we see activity that seems like it should be very far. And then here we ran a slightly more complex, the mixed effects version of this model, accounting for the repeated data from each subject as a random output. Takes a little bit longer, and then we actually get more robust activity in some brain regions. So here's what that overlap looks like. And then looks much smaller, but similar to the activity that Chris reported from his paper with all 10 subjects. So we think maybe we thought the model was correct. The caveat is we also ran a version of the mixed effects model that had this autocorrelation parameter that was in the tutorial. This is the one that took about an hour to run, and then it ended up looking like that, which doesn't look like anything, so maybe we won't actually have the R function. And that's part of our future direction. So this is certainly what the documentation is for some of the example models, and they're pretty different. Yeah, they're different and kind of incomprehensible and not very well explained. So that would be our next steps. For me personally, I'm at the point where I would not feel comfortable using the tool without probably calling Tom and asking her to explain to me how you actually parameterize the actual math algorithms. Alright, so future directions. So this is what people want to get feedback on this. Right now the tutorial is just for 4 subs on the verbal production task. We're considering remaking it to have all 10 subjects just to make the results a little more robust for people to look at. And potentially using Chris's motor task as we expect that to elicit even more robust activity. As I mentioned before, more details on how the models are run and how the stats are pulled out from there. It would be nice. Oh, no, I didn't do that. Okay. It would be nice to get a function that would generate the scripts to make the models. We also think it would be nice to get more details on how to handle the input data. Still a little unclear. There is no documentation on this now, so we're still unclear on what needs to be done differently if you're putting in raw pre-processed data versus data that's already been modeled at the first level. And the examples in the current Neuropointillist tutorials use both, but don't really explain like what needs to be done to account for which. So that'd be helpful for actually using the tool. The package is kind of weird, and why the installation was so complex. So if we could somehow make it really simple, that'd be great. Our mass creation pipeline has to be run manually through the command line. If we can integrate that into the pipeline, that would be nice. Part of there, the input files that explain the task are kind of complicated and non-standard. If we could switch that, that would be very helpful for folks. So we were able to get this working on our Macs. We tried it on Allie's Windows computer and it didn't work. So we're very sorry that the tutorial isn't helpful at this point.
Okay, the goal of this presentation is to keep it short and quick, and we'll just give you the highlights of what we've been doing. So that's what we're planning to do.
Go. Yeah.
So to give you motivation, when you are doing different modalities of imaging, it sort of can take time and effort, especially if you do multiple modalities. So to give you sort of a way of doing it, we wanted to do an autoencoder to potentially use one modality to produce another to extract other information. We've been hearing about that all week. We probably talked to most everybody about the project, and so we're going to keep going.
Oops.
So this is the pipeline that we had to work with. If it hurts your head, it makes us cry. So what we ended up having to do is to go through AWS. We set up a Jupyter notebook that we also had terminals through. Each of us had users on this Jupyter notebook that we linked up to our GitHub that we had all of our code into to help with version control, AWS, and to make sure we all were running in the same environment. So after that, we decided, ooh, what kind of data do we need? So we kept trying a couple different sets. XI didn't work. CMI did not work as well, and so we tried to go with HCP. Yes, queen. So with our architecture, we ended up using sort of the HCP data, going through the UNet, making, trying to extract the T2 data from it. We ended up, this is one of the results that we had in the CMI data when we were still using it, where we had the original T1, then we projected T1, and then those are the actual T1, which we had our L1 when we were training with the first epoch of around 0.15, which is okay to start with. This is a good toy example to sort of learn how to do this technique.
Yeah, I mean, we basically ran into the issue that the CMI data's T2 images weren't super great, so the model wasn't learning something pretty much. By the time we moved on to the HCP data, I think it was too late to actually train on the HCP data, so instead what we ended up doing was making a Python package that makes it easy to go and scrape stuff from the HCP Amazon S3 bucket. And it's in way beta form right now, and we'd love contributions. We'd love people who need any sort of functionality from this to submit an issue, submit stuff that you can do. We have like a tiny demo that hopefully works. Okay, let's see. Is that big enough?
Yeah, you're good.
Yeah. Okay, so we made this a pip installable package that works. And the main issue with
well, these are not real.
Yeah, I mean, we're still workshopping the name, so. No, these are fake credentials too, just to get it running. But the main idea is that getting the credentials running to connect to the HCP bucket is super hard. So we made this setup credentials function that just lets you copy in your access key, copy in your secret access key, and you're done. And then it allows you to scrape through data. So this is just to show that there's nothing in this data. And now for one subject, we want to get T1W and T2W images that are preprocessed and registered to the MNI space. So we can just call this one function that does that. So this is actually querying the Amazon bucket and scraping. And you can see that and you have those stored in that sort of format. And you can do it for a bunch of things, multiple subjects, only one modality, and it lets you do that for now. So we have a couple more functionalities right now, but it's definitely being, it's definitely still under construction. Let me move on here.
Any questions?
Also, if you need to quality check data sets, talk to me because I wrote some awesome tricks to do it in JavaScript and in like quickly outputting all the images. So for the CMI data or any large data.
Great. Thank you.
So we are giving an update on the ConvOuch project, which we plan to do brain CT image classification using a deep convolutional network. So our goal was just to practice skills to learn how to train simple convolutional neural network to classify brain CT images that either has having an intracranial hemorrhage or not. So we found this paper, and this is how they show their data set. So given each slice, it has labels of either having a hemorrhage or not, and also there are subtypes. So we were like, oh, this will be a perfect data set for us to play around and learn these skills. So when we start to look at it, what we thought how the data set looks like will be like this. So we are learning to bake something, and every ingredient is prepared for us, and we just need to mix the flour and the sugar together and then put the whole thing into the oven. However, after we download the data set, we were actually baking something like this. We need to produce our flour from the wheat and also got milk from that cow. So we modify, so here are some examples of their data sets. So there are like about 500 folders of their scans, and then each of them have different structures, and some of them have 4 scans, and some of them only have 1 scan, and some of them have 2, and also they all have different names. So we modify our original goal is just to change it to determine and select some usable scans and organize them in the BIDS format. So 2 days have passed, but we were successful in that. So now we have select all of the usable scans from each subject and organize them into a BIDS format. And also we have another folder that has this format that will be easier to feed into the neural network for further training. Now we can finally come back to our original goal, is to train a simple convolutional neural network to classify the CT images. And we decided to use a Keras pre-trained ImageNet VGG16 model. And this model has this big chunk of convolutional layers at the bottom. And then there is, on the top, there are 2 fully connected layers, and to do a classification task, which is saying which is one of the possible 1,000 categories. So what we did is we modified this model a little bit. We removed the top layers and we put our own fully connected layers, and then the final top layer will just give 2 classes. One is hemorrhage and the other is no hemorrhage. And also we freeze all of the weights in those previous early convolutional layers just to make sure it can be trainable on our local machine. So this is how the data look like. And then we also prepare the images a little bit. So the original original model will take 3 channels, red, green, and blue. And now we just create different windows of these CT images based on the luminance value. So there's the brain window, there's the bone window, and also subdural window, and they all provide different types of information of the tissues or like the bones, and they are supposed to provide complementary information of that is embedded in this CT scan, and all of them are feeding into this neural network and to give a prediction. So we also have coded a Keras data generator that can read this original data and directly feed into the neural network so that we don't need to think about, oh, how do we divide training data and how do we divide validation data. So we first started trying with 10% of the data just to make sure the model is okay, it can run, and it can overfit. And we did a great job. So for the training data, the accuracy reaches about 100%, and the validation is growing and then reach a plateau. So which is saying that, oh, the model is doing the correct work. And then we train with the whole data set, but we realized that our model crashed with the whole data set. We got a loss of none, which is infinitely large of loss that the model just don't know what to do with it. So what might cause the problem? So we asked different people, and then the major reason we thought is that because these are medical imaging data set, some of the slices are weird. For example, this is one like at the top edge of the brain that only a few voxels are white. It's almost completely black, so it may confuse the model. So what we did is we only used some middle slices of the brain instead of the whole brain slices. And then this is our most finished version of the model. I think at least during training is doing a good job, and then the validation loss is gradually decreasing, although the accuracy is not a lot, but we were just playing around with different hyperparameters, and we were also thinking about maybe we don't have enough data, we may need to do some data augmentation to improve. But we think it's a good start point as a beginner that we never worked with neural net before, and we got something running. We feel it's already a really good thing to be able to learn from this NeuroHackademy. Okay, so skills acquired. So we did a lot of data munging, prepared big data set for training, and also we both learned a lot of coding in Python, like these packages, Numpy, Pandas, MyBabel, to read the CT images. And also we learned a lot of different skills for machine learning, like Keras, and practice those terms that we only heard in lectures before, and now we know how to change them. And also we did a lot of Git and GitHub work. And tips learned, open data doesn't equals to usable data. So always pay attention to that. And high quality data is critical for all models. And also now in practice, we learn the term vanishing or exploding gradient. And we know in future work, we will pay attention to that. And also don't reinvent the wheel. Like, we were literally trying to program our own Keras data generator until Ariel told us that there is a Keras data generator that we don't need to program by ourselves. So that's it. Questions?
So we are the Brain Age group. So we were interested in generating a model that used brain data, both structural and resting state, to estimate age, and then applying that model to clinical populations to determine if they had advanced brain age. So we used an already available pre-processed data set on OpenNeuro, and they had 122 healthy controls that had usable structural and resting state data, and then a clinical group as well that was divided into 3 groups. There was an ADHD group, a schizophrenia group, and a bipolar group. And for the functional connectivity, we used 2 different parcellations. One had 197 regions and one had 444 regions, and we generated connectivity matrices. And we used that for our features for the resting state, and then for the structural, we used just the T1 weighted volume, the whole brain, for our features.
Yeah, so the main model we use is a support vector regression. So basically it's very similar to a linear regression, but you allow mistakes, you allow certain points to be misclassified so that overall it gets a high classification. And basically you're trying to predict age from these input vectors you just showed, that the resting state has about 20,000 dimensions, and the T1 has about 2 million dimensions. So yeah. So I don't know if you're all familiar with grid search, but basically there's many parameters in this support vector regressor, so you can try out many different options and see which performs best. So that's what we did here, and we tried using the 2 million features, or using just let's say 100,000 features. And we tried out different C parameters, which are the amount of mistakes you'll allow to make. So we had this data set of the CMP data set, and we basically split it in 70-30. We did everything with the 70% of data, which is about 84 subjects, and then we have this 30% that we haven't looked at yet, and we probably won't unless we decide to finish the project. So with the 70%, we did this grid search. We validated. We tried to find the highest accuracy. And then we have the clinical data, and we split this in 50-50 as well. And what we're going to show you today is basically using the validation set and the 50% of the clinical data. So let's see what happens with the healthy controls. Here, what we're trying to do is just train a model where we give it this brain data, and we're trying to predict the age and healthy population. So how well can we predict age? The structural functional results in better prediction.
Yeah, so what we found was that our functional resting state model with the 444 parcellation actually predicted our model the best. And so we only had an error range of 6.4. So if your true age is about 30, you would have a brain age of 24 to 36 or so, doing that math right. And so this was better than our parcellation of 197 and our structural data. Then we looked at our clinical population. So we had data from 139 individuals. Some had ADHD, some had schizophrenia, and some were bipolar. And we were curious if they showed more advanced or more delayed brain aging. And so normally you would expect more delayed
brain aging in these populations, maybe not ADHD, but in the other ones. But our model showed a reverse pattern. And so actually our model, the better model that we had earlier, showed that your brain age would be less than your true age. So for ADHD, our mean age was about 34, so our model would predict you to probably be, your brain age to be about 31. For bipolar, that would be 31 as well, and schizophrenia would be about 28. And so this was obviously different than you would expect. We only had, though, 140 people. The study that we were kind of trying to replicate had like 2,000 people originally, so there could definitely be some differences in that.
Oh yeah, so we just ran, I just got a new result, so we wanted to show it. So this is, we were showing before was the CMP data set, but we also just finished cleaning the NKI data set, which is a little bigger. So our previous results may be biased by the distribution of ages, right? If the model's trained with a certain short range of ages, many ages around the mean, then you try to predict, clinical populations, which are very different ages usually. It may not work as well. If you have a lot of data, that's okay, but if you don't. So basically, now we have this new data set, and we haven't been able to run everything, but we just, so we can go on the next slide. So now the question is, if you train a model, you say, hey, I can predict your age from your brain data, I can compare your brain to the normal population, I can say how old your brain is, regardless of your chronological true age. Well, if you were to have that, how well would that generalize to another data set, right? So can the CMP model predict ages from the NKI data set and vice versa? So it turns out this, Hector rechecked the stuff, because I just got it, but CMP doesn't really predict well the NKI data set. It'll give the right age with a margin of error of 16 years. But using the NKI data set, you can predict reasonably well. And this can be improved. We haven't done grid search on this, so yeah, this could be improved, right? So yeah, you can predict it with like 9.6.
Sorry.
Just kind of overviewing what we learned from this experience. So these are kind of how we felt and how confident we were about our skills before doing the hackathon. So you see our confidence level from a scale of 0 to 10. Also, just confidence does not equal capability. But, and then after the hackathon, we felt like our kind of capabilities had improved. Jupyter Notebook improved. AWS was finicky, so we're really interested in what the other group had been working on. NiLearn, scikit-learn, which actually was a lot of Daniel. I had his face on this earlier, but he removed it. Python and Bash skills improved. So overall, we improved a lot of the skills, so it was really helpful. And we just want to thank a lot of people who scraped a lot of data for us and shared it with us and just guided us along the way and helping us learn how to use Git. So thanks.
So we are the NiFET pals, and we're kind of two groups become one group, and we have two projects that we've been working on. But altogether, we've kind of been trying to offer each other support for NiFET. Okay, so Josie and I have been mostly working on the PALS pipeline, and here were our goals for the hackathon. To learn about NiFET, to work with Git, GitHub, Docker, NiLearn, and hacking, and most of all, to have fun. So here were the tasks that we were trying to do for this week. Okay, so the first thing was when we were trying to get PALS to run, it turned out that we had a lot of dependency issues because it's still running on Python 2. And so we decided we would try to Dockerize it, but it turned out that making the GUI show up through the Docker was a non-trivial task. Josie was able to really figure this part out. So this is what the pipeline, or the GUI looks like in the Docker now. Okay, and then we also added a README file for putting up a Docker. Okay, next we were finally able to get into trying to refactor PALS with NiFET. But it turned out that this was also not trivial because the GUI, it was an interactive GUI, so we couldn't just wrap all of our functions into NiPipe. So we had to kind of break it up into different parts. So we decided we would just start with one of the modules, which is really just doing brain extraction, and try to work with NiPipe there first. And it was successful.
Yay.
And then also we, when we put NiPipe into the Docker, we also had some issues with running FSLIs in Docker because there was an issue with NeuroDebian. And we had also wanted to improve images in the PALS toolbox. And so we decided to just try to get rid of FSLIs and move into NiLearn. And this is what our QC page looked like before. And okay, so that's pretty much it for our future stuff. We have a lot of things that we would like to work on, including moving into really, setting up continuous integration, testing, and then also just finishing up the things that we started this week.
Special thanks to Michael.
Yeah, special thanks to Michael for helping with the NiPipe and NiLearn so much, and this group here, support, and just everyone here.
And then we have one more.
Yeah.
Well, start in the beginning. You got this?
You start.
Okay, so the virtual brain basically simulates a bunch of neuromass models. For those of you that's not familiar, this is what one of them looks like. It's just super complicated, non-linear, and ugly. And it has a bunch of local parameters, global parameters. The H, A, K, E, all that sum is your structural connectivity being fed into it. It's not nice to look at. Basically what we're trying to do is...
Don't you go down?
Oh.
But I think you have to click it.
Okay.
It's annoying.
Yeah. So, yeah, so what the virtual brain does is the user gives all the parameters, the DTI data, and it spits out functional connectivity. And you can optimize the model to fit better to what your subject's specific connectivity is. Actually, I have to click it.
Yeah.
Okay. Yeah, but these simulations are really slow because based on your parcellations, some people can have 200-something brain regions, and then you have like 10 subjects or 50-something subjects, depending on the size of your experiment. And if you want to explore all the parameters, it takes forever. So we came up with a verb for NiPiping, which is NiPipetting, for all these simulations, and we try to do that to make a workflow to wrap around virtual brain. So one thing we ran into was that each NiPipe node has its own function environment, which means we have to import all the packages, modules inside of each function, each node. It was easy to solve, but we just do a bunch of mathy and signal-y stuff, load a bunch of stuff, and then we figured, oh, virtual brain is still stuck in Python 2, and it's not too compatible with NiPipe. So we had to save all of our outputs to each folder as
Pickle
files, which are just strings that we pass along, and at each node it has to reload the file after it gets the string. That's just what it does, and what's happening? Okay, actual code for NiPipe. We should have done all this. So finally we did all the wrapping for the virtual brain, and now we're ready to look at our workflow. So this is what the simple graph looks like, pretty decent. So as you can see, we load in the structural connectivity, we feed in the parameters, and then normally what would happen is it would create the structural connectivity, and then serially it would create the monitors, the integrators, and the models. But with NiPipe, it does it at the same time. And here's what it looks like if we actually do a real simulation with numerous parameters. We were kind of like, woo! Yeah. And then We actually ran the workflow. Everything worked out pretty well after 3 days. It took a while. So yeah, we actually this morning did a data dump for all the outputs, so now it looks nice and clean. So we're proud of that. Do you want to do the simulation things first?
The widget? Yeah.
Wait,
still on the same one. Yeah.
Okay. I forgot.
Yeah, and then, so we spent most of our time working on NiPipe, but one other thing we were interested in doing was making a little widget for actually viewing the simulations once they've completed, because what I normally do, for example, is do a 2D parameter exploration, so 20 different values of one parameter, 20 different values of another parameter, so you're getting 400 different simulations just for one subject. And so we just wanted to make a nice visualization for that, so we made a little widget, which you can see just here. So these are your 2 parameters, and then, so this would just be for one subject, and then, hopefully it works. Yeah, so you can just change the value of the global coupling and of the noise, and then you can see pretty quickly what the simulated bowl time series looks like and what the simulated functional connectivity will look like. And so we want to thank everyone. Special thanks to Michael and Ross, Kirsty, Tal, and Sacha for helping the pals. And yeah, we had a really great experience. Thank you.
Can I ask a question?
Yeah.
All the pain that you had with getting the visualizing into the Docker. I have 2 questions. One, how likely are other people going to visualization? I'm dictating to Wikipedia right. How likely are other people to run into those problems? And if they are, have you written up everything that you did to make it easier for people?
Yes, we have a README on how to do it.
That's so cool.
We really wanted to make it very big.
Yeah.
Especially for people like us, because it's such an easy thing in the end. When you see it already, you say, well, it's not that difficult. But we spent like one day, whole day trying to do this. So.
Yeah, it was like a wild goose.
Yeah.
But yeah, we really just wanted to make the pipeline like accessible to as many people as possible. And so we're gonna actually try to make it so that there is a Docker version, but we also want to make it just normal, so people can do it either way.
Okay, cool. Thank you.
Yeah, so we spent the week analyzing the study forest data set. So this is an open fMRI data set in which people were continuously scanned while they watched the movie Forrest Gump. This was initially released as a 7T audio-only data set where people were just listening to an audio version of the movie. This is in the first issue of Nature Scientific Data. But since then, they've released a lot of extensions, and that includes a 3T data set where a subset of the original 20 subjects were rescanned while they watched the actual movie, and they kind of collected eye tracking data, and they've done a lot of annotations on the data set. So this includes characters present in the film, and this is pretty fine-grained, so it allows us to basically pinpoint every single instance of each character, not only characters that appear a lot like Forrest himself, but like the single instance of President Nixon, for example. And there's also a comprehensive annotation of emotions portrayed by characters in the film, and this is also a really, really rich resource, so we can point to an ATR and know that at that moment a character was expressing shame through gestures, or that fear was being conveyed through the context, for example. And we'll talk more about kind of like the task-based analyses that utilize this resource in a bit. But in general, so we approach this just as an opportunity to gain some experience with open data sets, and also just do some analyses that we hadn't gotten the chance to do with data that we've actually collected ourselves. And what we kind of converged on were some analytic approaches that kind of compared different measures of similarity between subjects. So this included like inter-subject temporal correlation in the fMRI signal, but also similarity in people's kind of perceptual behaviors with like the eye tracking data, and also similarity in their actual neural representations for different characters and for different emotion categories. So, yeah, I'm not going to go into this detail, but basically, like I said, the main kind of measure of interest that kind of started us off is just this global measure of similarity in the neural time course between subjects. So basically, this involves just performing a whole brain parcellation, extracting time courses from ROIs, and then correlating those time courses and just getting a single average value per dyad. And then you can usually visualize that in a matrix like this. But like I said, one thing that we were interested in doing is kind of characterizing this a little bit better by seeing how it related to or predicted kind of differences in sort of like spontaneous attentional and perceptual behavior. And how we did this was made use of the eye tracking data. So that was collected continuously throughout the movie. So for any given TR, we have a measure of where people were looking on the screen. And basically, we just use this to compute a raw distance metric, just Euclidean distance between like the points on the screen where pairs of subjects were looking. And then averaging this together, you just have this kind of very coarse representation of differences in how kind of synchronized people's eye movements were during the scan. And so these DMs are a little bit smaller than the one I was showing you earlier because we did have to remove some outliers from the eye tracking data set. It's actually sort of amazing. There were people who were apparently just looking like the exact opposite of everyone else for the entire movie. So related to that, in the interest of scientific transparency, here's the very insignificant correlation that I ran between those two measures. But there's some more fine-grained ways that we looked into it as well, and Jim's going to talk about that now.
Cool, so another topic that we were interested in is the neural representation of characters and how these representations are formed and how these representations change over time across people. So one hypothesis is that the more you learn about someone, for instance, Forrest here, there's like Army Forrest, there's like Ping Pong Forrest, there's Bubba Forrest, there's Kid Forrest, there's Runner Forrest, there's a lot of Forrests. But then as you learn more and more about Forrest, your representation could form just like one Forrest. However, a competing argument would be that everybody starts out with kind of like minimal information about Forrest, but then as you learn more about Forrest, everybody brings their own kind of individual personality, and in the end, everybody just has like a different representation of Forrest. So we decided to test this, and the way we did that is we computed a data map that's representing Forrest for each subject at each run. And we can compare the similarity of these beta maps that represent Forrest for each individual across all the individuals and then grab the average of that. So we can do this for run 1, and then we can do this for all the runs up to run 8. And when we plot these averages across all runs, you can see that it does seem to look like that there is a linearly increasing trend in terms of the similarity of Forrest representations. So this suggests that like the more you learn about Forrest, we kind of like converge on this mental representation of the Forrest. And so we were curious, whether this just happens for Forrest or does this also happen for other characters as well. So another significant character that appears a lot during the show is Jenny, who Forrest gets married to. And you can see that for Jenny as well, a lot of people have this convergence of the mental representation of Jenny. We also looked at some other characters that don't appear as often, such as Mrs. Gump or Bubba or Lieutenant Dan. And for these characters, you can see that there is not much of that linear trend that kind of increases over time. Possible confounds. We thought maybe, is this a result of just like the whole brain similarity, just like converging across time for everybody? So this is the whole brain intersubject correlation similarity. And you can see that it like bumps up and down for certain runs, but then it does not have that kind of continuously increasing trend. And we also try to see it, can we see this kind of pattern in the eye tracking data? And then in the top here is similarities in pupillometry or pupillary responses, kind of like a measure of arousal. And you can see that it's very similar to the ISE, the brain representation similarity over time, but still it doesn't have that kind of increasing trend. The only thing that does kind of have a trend is eye tracking distance. So this is distance measured that gets smaller over time, suggesting that as time progresses, people are kind of looking at more similar locations over the movie. So in conclusion, this happens.
I'm going to talk about some of the work I did on this data set with emotion. So
Jin and Jeff did a nice job of covering different representations of characters, and I was interested in the same thing, but with our emotions. And so just a quick recap of the goals. I wanted to see how different emotions were represented between individuals. I want to see how this changed throughout the course of the movie, and then just more broadly, if we could derive sort of this taxonomical structure of emotions based on their neural representations. And a quick note that at the biological unit of focus for these analyses was at the network level, because there have been recent papers showing that this may be a little bit more privileged than looking at the ROI, or certainly at like the voxel level, at the voxel level unit. So I picked 5 networks that have been shown to be implicated in emotional responding, and because I already had the parsers for like a different analysis, which is convenient. And so the first thing I did is I just looked at the mean inter-subject correlation broken down by each emotion. There were some kind of surprising findings. I would have expected more basic emotions like anger, fear, and sadness to be relatively high, and that these are like very old, conserved psychological processes, but instead it seemed to be some of the social ones that have some of like the highest, inter-subject correlation values, like pride and shame, that kind of come about in the socially evaluative context, which is really interesting. And then to sort of further unpack these, I decided to like plot out all the full matrices, and so we see that some of these, like shame, like I said, has like a very high outside of 1 or 2 weirdos, very like high ISC, but some of these other ones like anger and even sadness are like kind of weird. There's no like consistent pattern or structure. This also seems to be the case for things like love, which is seemingly random. Now I wanted to look at how this changes across time. So certain emotions show like a downward trend in terms of their ISC, like shame, and some like I think gratitude show a general upward trend. Some of them are kind of opposite, like I find it kind of interesting how anger is followed by a spike in happiness, and then for both in the beginning and the end of the task. And then I submitted some of these, and then I submitted just like univariate patterns of activation to just a clustering algorithm to see if we could come up with this taxonomy of emotional representations of the brain. And some of the results were kind of weird. So on the one hand, I'm happy that compassion, love, and happiness are in their own little cluster over there, and kind of concerned that sadness was thrown in there. Happy that like fear and shame are grouped together, because maybe that's what we would expect based on valence, but kind of interesting and also a little wacky. Oh, I guess.
So this data set is really nice for 2 reasons in one very short minute. One is the annotations, and the other is that we have 3T data and 7T data. And it would have been really cool to look at all these analyses on 7T data. It would have been really cool. Previously, I had an experiment, which I won't go into because there's no time, that looked at the 3T data, and I wanted to see whether the results replicated in the 7T data as a basis for looking also at the newer results. What actually happened is that it took a lot of time and a lot of help from Ariel and Mikael, and thank you both very much. But now the data is pre-processed and accessible through Jupyter Hub inside a Docker container, which is a start. Just to say that a small analysis on a very small subset of the subjects and runs gives nothing so far. So far I can say that I have not replicated the 3D results with us. And thank you very much.
Yeah.
With background, where we began.
Yeah, so where we began, it's a toolbox that worked just for me. It wasn't adapted to anything else. But the idea was, yeah, as you also will see later on, is that you give you the statistical map, and it gives you out figures and tables. That's the short background.
Yeah. So we kind of decided at the start of the hackathon to join on and try and make this something that was a little bit more robust and compatible with other individuals who weren't Michael living in Switzerland. And even though we'd all like to be able to run up and ask him questions all the time, as we've been doing for the past week, that is not always possible.
So we took on the task of kind of packaging it as a little standalone Python package so that it would be installable for others and ideally usable. And so we kind of started, we were all working together, and then once it got packaged, we were like, oh, there's a lot that still has to be done with this. And so that is when Dan took the lead and kind of came up with all of this. So Michael and I are going to kind of stand here and let Dan take over now.
Yeah, so this project's still very much a work in progress, but I put together this little notebook here, kind of walking through a use case here. So for instance, you have a stat map and you want to identify what clusters there are and the peak voxels within those clusters. So I just pulled off a stat map from NeuroVault using NiLearn.
Text bigger, please.
Text bigger. Oh, bigger?
Yeah.
How's that?
Solid.
Okay, so what we did is we made this compatible to run just straight off the command line. Ross did a lot of work on documenting kind of the arguments that you can provide into it. So you provide a stat map or a file, and then also you provide which atlases you want to use to identify the cluster or the peak voxel. And then you can also threshold your stat map as well as the cluster size. So you only want to look at clusters of a certain size. And as well, when you're using a probabilistic atlas, you might only want to consider labels that meet a certain probability. So you wouldn't want to look at, you wouldn't want to have labels, say, for instance, that have a 5% chance of it being the case. As well, this script basically spits out a ton of files. Gives you images of the clusters themselves, as well as a whole bunch of the atlas information. So you can specify an out directory there. And so I've already run it to avoid a live code demo. But you can just run it straight off the command line. You enter in the arguments. And after it spits out some warnings at you, it produces that collection of files. So like I mentioned, you can have all these images, which I'll show you in a quick minute here, but then it also has all the information about the peak and the clusters, so kind of what the peak values are and what their labels are. So if I just read that file in, this is what came out of that example there, and so you can see I have like the cluster ID, the peak location in MNI coordinates, as well as the cluster mean and the volume size, as well as kind of the label according to, in this example I used the Harvard-Oxford Atlas, and so the labels according to that, and the probabilities as well. I'm working on cleaning this up because you'll notice that this is actually like two tables into one, and so we're working on splitting this up and making it more user-friendly. So if someone wanted to read this table into their own script using pandas, they could without any hassle. So,
it's also quickly to mention, because I'm not sure if that's so clear, but the peaks gives you just gives at the particular location, like, okay, this is 20% most likely a frontal lobe, 30% something else. And the cluster percentage, or the labels in the cluster table, is giving you, if you have a long cluster, it says, okay, 30% of that is in the frontal lobe, 20% is going in this other region, and so forth.
So this is just these are some of the images that are included or produced, and the cross is just focused on the peak voxel there. So it allows you to kind of quickly scan through your clusters and visually check to see where everything is. And so of course you can just call this directly from Python. We worked pretty hard to get documentation for each of the functions, and so if you wanted to call this within an existing Python script, you could. And yeah, so you can basically, instead of calling it directly from the command line, you can just use this create output function to get the exact same thing. So I think that's that.
Mm-hmm. Well, we have, by the way, yeah, if you want to participate, can you go to the GitHub page?
Yeah, so kind of future directions, and if you want to participate, we have some open issues right now, and feel free to start contributing. Yeah?
Yeah, thanks.
Okay, so we did NiLearn task networks, and we pulled from a lot of open source things like NiLearn, Open Neuro datasets, and Human Connectome project datasets. And they all had really cool logos, so we wanted to create our own logo. So we are NiTask Connectivity, and we also wanted to include NiStats as logo, but they only have an alpha version. And Tal, maybe you should make a NeuroSynth logo, because right now you don't have one. You can steal it. You can steal it.
You just took a picture.
So we don't have any other slides really. So we're going to switch to our GitHub. Is it big enough? There we go.
All right. Yeah, so the main goal of this project was to teach ourselves how to use NiStats and NiLearn, and then track it along the way and write a tutorial. So predictably, we ran into lots of hiccups along the way. But we do have kind of our rough run through, and we'll go through just a couple of parts of that, but respect the time as well. So, and I set this on Slack as well. We ran 2 different data sets, so Human Connectome project, NBAC data. Definitely could have used the easy HCP. This probably took up like half of our hack time pulling the right data and sharing it and processing it and all that. And then we also used Open Neuro data set on listening to positive and negative music, and there were 2 groups, those with major depression and those who were controls. And so we got kind of a very quick just steps we went through. So NiStats is the processing part to get ready to use NiLearn for connectivity analyses. And the NiStats part is within the data processing and signal extraction notebook. Won't go through that here to save time. So yeah, we could jump into Carolina.
So yeah, so we have 2 goals. We wanted to compare 2 task conditions, but we want to take a 2 different approach to this. First, we want to have first approach is more standard. So we take Atlas, brain parcellation from literature. Like you can take whatever you want. We took Power Atlas, Power ROIs. But another approach is to take ROIs from activation maps, statistical maps, and what we did. We also did this, and maybe first I will show you some how we sorry. How to like 2 fingers. Two fingers. Okay. Okay. So yeah. So there is a pipeline step by step. First, we create parcellation, the same way as for a resting state. We extract time series for each ROI. We generate design matrix because we have to have onsets for each task condition. And here I show you results from comparison of 1-back and 0-back and 2-back task from Human Connectome project. That was 33 participants. So then we filtered time series and split them into time series which are related to 0-back and time series from 2-back. And then we calculated correlations within these 2 parts. And we did simple statistical tests. So we first vectorized matrices. We ran a simple statistical t-test, paired t-test to compare each edge. And then we thresholded it with FDR, corrected this for multiple comparison using FDR correction. And you can see a differences. These are differences. So this is contrast between. These are t-test values between 1-back, 0-back, and 2-back, and these are corrected for the multiple comparison. And then we, sorry, this is some error, but ignore it. Then we wrote a small function to visualize results. So here are results for. So here you can see how many edges were different from 1-back to 2-back. And to which network it belongs. And then maybe you show your results, because it's also very exciting.
Well, yeah. They're cool looking. So the next analysis pipeline we tried was with the using the activation analysis and then taking the peak coordinates from the activation analysis. And for this one, we used this other data set, this emotion music data set. We found it cool because they had depressed patients and also controls, and they made them listen to positive and negative music, and then we had the chance to compare them. So the cool thing is that with this notebook, we can just stick this data and then just do some pre-processing and create our model, and then already like in 5 minutes or so you can see the results online, which is really cool. Here we look at the results from the combined groups, meaning control and patients, depressive patients together. This is the activation map for the negative versus baseline. This is the activation map for the positive versus baseline, and then this is their contrast. And then using the activation maps and the peak points, we got those signal and extracted those signals. But it was kind of tricky to extract the signals from those voxels, because most of the times they are overlapping. And this was like maybe one thing that we spent so much time, and it was solved last night at 1 thanks to my call. And then we could get rid of some of those overlapping voxels and then extract the data, and then we can already see in a couple of lines some connectivity matrices combined for different groups, and then also we can get the time series specific for each condition and group, and then we can already have some statistical tests. So here, for instance, we can see the connectivity matrices for those peak ROIs for negative music and positive music, and also for depression patients. And after the statistical analysis, what we could retain was only 2 edges that were statistically significant for depressed patients, which is kind of cool, because here, for instance, this is a widget that we really enjoyed looking at with our peak voxels. And then here we can see the only statistically significant activity, which was for the depressed patients when they were listening to negative music. They had higher activity they had higher functional connectivity between their putamen and insula, and between their insula and auditory cord. No, what is this?
Temporal pole.
Temporal pole. Yeah, we got those regions by sticking in the coordinates to neurosynth, like in very short time. And then these are other connectivity matrices, again using like 1 line of code, and you stick your matrix and then your coordinates, and you can already get these cool plots easily. Yeah, I mean, we don't want to really overinterpret those results, because probably they are wrong, but it was really, easy and fast to see. Just stick the data and then do the analysis, and then get your connectivity matrices like in a couple of hours. So if you want to do the same thing, you can just go to our repository and then play around with it. Now we have maybe a couple of more slides.
Just 2 more, and they're funny, so it'll make everyone wake up. Okay. Oh wait, I shouldn't give it away. Okay. 2 seconds while it loads. We learned a lot from this experience working as a group, and once this loads up, okay, thank you. So first we learned that GitHub is kind of hard, but we had a lot of support from Kirsty and a lot of other people, and we definitely did lots of all the messed up things that you're not supposed to do, we did, and I think we fixed it by the end, but it was an experience. Open data sets are great, and we had a lot of fun combing through a lot of different ones, but at the same time they can be kind of hard to deal with, and we had a lot of trouble downloading HCP data, so that group that did the HCP thing, super awesome. And creating reproducible pipelines is fun, and a Python. And thank you to everyone, especially Chris, Gael, Tal, and Michael for help. That's it.
Thanks, everyone. So we called our package Fragmenter. It's kind of building off of what Michael had developed originally, but
we basically wanted to take cortical maps and hyperparcellate them, or take a surface and build a random parcellation from that. And the vision was that in a typical connectivity analysis, you compute some graph theory metrics, and we wanted to see if there were any sort of bounds on metrics that would be computed if you build smaller and smaller parcels. And the output of this can just be plugged into any basic connectivity analysis. And then we'd also thought that it might decrease processing times for various tools like Searchlight, FDR, where you might search over all voxels or all vertices, and now instead you just search over parcels. So we're going to go through a little demo. It basically just takes on a surface. You get the mesh and the vertices and the faces, and you plug it into a class called Fragment, and you supply the number of clusters, and then it has a pretty color option if you want to plot pretty colors. And then, so you fit it. We tried to model it after like the sklearn model that's like fit, predict, whatever. So you get whole brain is the object, and then you fit it with the vertices and the faces, and it essentially spits out a cortical map. And this example was just run on the whole brain surface. So we're going to get a random parcellation for the whole surface. And I think this is interactive. Yeah. So, I mean, that's all fun and dandy, but we also want to take a given cortical map like the Desigan-Kiliani Atlas or the Destrio Atlas, and then hyperparcellate the existing regions and respect the boundaries that have already been defined by anatomy to some extent. So you basically, in this case, supply a label map. You retrieve all of the indices for each existing region, and you feed that in along with a list of regions that you're interested in. So in this case, we're going to look at the temporal lobe. And you generate subparcels for each of the temporal lobe regions like this. That was inferior, here's the middle, and here's the superior. And they respect the original boundaries, which is what we were interested in. And yeah, that was pretty much it.
And by the way, this demo is part of it's in the repo, and we also decided that this was not enough, that we wanted to benchmark the different algorithms that we're using. So I want to run you through that extremely quick. So as you demand a parcellation that has more and more clusters, you expect the runtime to be also longer, right? So we have 3 different algorithms, GMM, K-means, and Ward. And you can see that GMM really starts getting really slow, really quickly there in red. But Ward is pretty stable, and K-means is pretty fast, and then kind of matches with Ward later on. But that's just kind of one way of looking at this. Time to compute is not the only thing that you're looking for. The other thing that we can consider is stability. So here in the colors, if you see something, we computed 10 parcels with each method, and we saw how well they agreed with each other. And if you see red, it means that they agree a lot, otherwise not so much. And you can see that GMM agrees pretty well, but there's a little bit of random component there. K-means is pretty variable. They're in the middle here, but still 60% on average. And then Ward is extremely stable, and that's computed with a parcellation at 10 clusters. But you might be thinking, well, what about if I do 100 or more, and that's the answer? Now, Ward is at the top, and is still extremely stable, which at that point, since Ward maintains the amount of time it takes to compute, that's pretty cool that it remains pretty stable compared to the other 2 that become more and more variable. And this is also in the repo if you want to play with the code in both cases, or if you really want to play with the spraying, which is really fun. Yeah, so in conclusion, things we learned very quickly. Do you want to say that? Okay. All right. Does anyone want to say that? Anyway, we learned tons of shit, question mark. Thanks, Kirsty, for the help. That was really fun to see her trying to fix Christian's problem. Moving from R to Python, that's missing a question mark as well. I tried. Writing object-oriented code, properly packaging and distributing software, collaborative coding, that was really, really big and really, really fun. And that was mainly from Christian. He took like
Yeah, and thanks to Ariel and Tal and Kirsty, and then Michael, obviously, for the inspiration, and Ross for all of the Git help.
Yeah, that's it.
Okay, so we were working on bidsQC, which is basically a way to check data that's already bidsified, because there's already a bids validator that can tell you whether or not your files and file structure actually meet the bid specifications, which is really important. But because it checks each one individually, it doesn't check across to see whether or not they meet kind of what you're expecting as the experimenter for your particular study. So that can lead to some problems in your data set that you need to catch. So one of them is duplication. So for example, you may have two files with different names, but the content of those images is actually the same. So if something got copied over and then someone's doing something horrible like manually renaming files and rename them wrong, you want to make sure that you catch something like that. You could also run into a problem where you don't have, for example, a run of a task, so you're missing a file. And this could either be for a good reason, like you didn't collect the data, or because it wasn't copied over, or for whatever reason, but again, you just want to know about this as the experimenter before you're doing your analyses. And then the last big problem that we wanted to address was if you have extra files. So this is where the content of the files is actually different, but for example, they might be listed as 3 runs of the go, no-go task, whereas you really only want 2. So maybe you started and stopped the scan, so you have like an actual fragment of one, or something else got copied over. But again, you just want to know that what you as the experimenter expect, which is 2 runs of this task, is not what you actually have. So what are you going to do about this? We wrote a little function that's going to be integrated into PyBid. So it just creates sort of user-friendly data frames that tell you about your data. And so you just call this validate sequences on a bids layout object. And it tells you whether or not you have any files that have duplicate content, whether you're missing files, or whether you have more files than expected for a given subject. And the way that this happens is there's just this configuration file that you can adjust. So you would just fill this with the information for your study. So for example, with our functional task, we're expecting 2 runs during the first time point, which we call wave 1. And it's just a bold sequence, and then our task value is go, no, go, and this one maps onto the naming structure for bids. And then we can also do it for the data map, for example. And the way you do this then is you just call, you get this layout object, or call whatever you want, and then you just run this validate sequences on the object and on the configuration file as inputs, and you can assign the output, which is 3 data frames, to whatever you want. And it runs on all the subjects that are specified in your bids data. So the first thing you get is this duplicate file table. And the first column is the content's kind of like unimportant, but basically what you're looking for is matches. So for example, rows 0 and 1 have the same hash. So that means that those files, the content is actually the same. And I kind of cut off the file path there, but that's because I copied the first subject's data to make the second subject's data for this example, so all the files are the same. And then you also get these 2 summaries, which are like the file count summaries. The first one just gives you all of the subjects and tells you what you have, and then the second one just tells you the problem subjects. So it basically just subsets it for you based on the value in the problem column. So this just allows you to really quickly scan through and say, like, do I have any problems in my data set that need to be addressed? Do they match with like known problems that I have in the data when it's collected? Or is it something that I need to go back and change to figure out what's going on with my data? And with that, I just want to say thank you to everyone who helped work on this. James isn't here, he helped a lot. Also Christian and Lee with writing the code. Tal and Christy too for the code and conversations. Also Grandma Shirley, who provided hours of entertainment while we were coding. And everyone else here in NeuroHack, so thank you.
Okay, so if you remember correctly, or at all, we had our nice workflow with something missing there. Now we have the same workflow with something there, which is BIDSonym, our newly created bids app that allows you for your special participants with their super special thoughts to be de-identified, more or less. And we were starting out with different tools. We plan to do PyDFace, the de-identification toolbox, and MRI DFace from FreeServer. Then we
already knew that the de-identification toolbox runs on Java and C++, so that was out of the game. But then luckily Satra pointed us to QuickShear, which is implemented in Python and NiPipe. And we successfully managed to integrate all of these tools. So on top left, you have the original not de-identified T1 image, and then for each of the different algorithms, the de-identified version, which you can already see kind of varies strongly. So because MRI dephase basically just scoops out the eyes. So if you go on our Slack channel, #BIDSonym, you see awesome 3D reconstructions that are haunting. QuickShear makes a nice clean cut, and PyDevice kind of like brings in some sort of angle. So, and yeah, of course our goal was to create a new BIDS app, which we did. It's out there. This is our GitHub repo. Hopefully this works now. Yes. Where you will find everything from our main function to Docker file, issue templates, contribution guidelines, and whatnot. We also have an Open Science Framework page for our BIDS app. And yes, also the BIDS app since yesterday?
Yeah.
Yesterday?
Yeah.
Updated this morning, is already on Docker Hub, so you can just pull it and start de-identifying your images. Yeah, so just so that you know what's with the color and the 4 cryptic letters there. Everything currently is just hosted on my GitHub account and Docker Hub. But of course, Rita and I did it together, and that's Rita's tech. So we hopefully plan to somewhere in the near future just migrate all of stuff to the big INCF BIDS repos. Oh, sorry. Double clicked.
So one of the things we were trying to do is use ReproZip to make our Docker image smaller. Claire was able to actually decrease it by like half just by chopping out some stuff we didn't need. But right now it is about 8 gigs big. And I was able to play around with ReproZip a little bit and make a tinier version that's around 400 megabytes instead. But then when I try to actually run it, I get a fatal Python error. So I don't know why. I think it's probably a bug of ReproZip and not me. So that's probably something that will need to be addressed in the future.
So yeah, basically, the whole BIDS app was done like on Wednesday, and since then it's just trying to get ReproZip to work.
We thought we'd be done yesterday by lunch and
Yeah.
we'd just like hang out for the rest of the day.
No.
Yeah. Yeah.
It's an experience, a learning experience.
Yeah.
So yeah, that's good, right? Do you want it?
Sure. Yeah, so like I said, in the future, we're going to try to work with ReproZip to get a little bit tinier. We also want to optimize the actual construction of the Docker image itself and add more code there. And then, of course, it never stops with the testing and the coding and the testing and the coding. And we'll be turning to Grandma to help us get through those sessions from afar.
So maybe some of you already got this, but we and some others started a cult following this grandma playing Skyrim on YouTube.
Thanks, Claudio.
Thanks, Claudio. And yesterday, this is the picture Chris already showed, we sent out a tweet mentioning her feed because we were always looking like for 6 hours at her YouTube feed, and she liked it this morning.
She liked it.
We did it.
We did it.
That's the best thing.
We did it. Okay, we're done. That's our peak.
Okay. Yeah. Oh yeah, maybe we should show you how it runs, right? Oh man.
Yeah.
Totally forgot that. Sorry. That grandma thing got me so excited though. So basically, yeah, it's a classic increaser, right? Classic BIDS app. You say Docker run, interactive mode, remove it after running. You mount your path to your BIDS directory where like images are you want to de-identify, mount it to BIDS dataset or whatever folder in a Docker image. You run the BIDSonym BIDS app, say on which level it's to run, either participant or group.
which the identifier to use, PyDphase, MRI dphase, or QuickShear. You can say, okay, delete the original raw data, which is not de-identified, or if you want to keep it for later rerun, in case things doesn't work out, you can also say, okay, no deletion and will be ported and copied into a derivatives folder. And then you can, of course, specify participant labels. That's that. Make sure to follow Grandma on YouTube.
Yeah.
And Twitter.
Yeah. Thanks, everyone. Thanks, Grandma.
Thanks, Grandma.
Okay, so we did some interactive data visualizations, and we did two sort of different things. But this is the data we used for both of them. It's from the ABIDE preprocessed data set, and it's so basically we did a seed-based correlation with the thalamus. And this was something I did for another project. But this data, by the way, has both autism and typically developing individuals. And in autism, there's some differences in the thalamic connectivity with different regions of the brain. So based on previous studies, that was the region of interest that we're looking at. And so we want to associate that connectivity map with this continuous measure of autistic social impairment, so social responsiveness. And so for the first visualization, we're looking at a multivariate approach where we make a predictive model predicting the SRS from those connectivity maps. And then we'll get a predictive map of the weights for all the training data. And then we apply that map to the test data, connectivity maps, and then we can get some predicted values. And the model we use for this particular example is, well, we just basically assume that the SRS is like a linear combination of the maps with some weights and then an error. And we just use the elastic net to estimate those weights. And the elastic net just has the like the least squares loss function, and then it has this penalty term, which is like a weighted combination of the L1 and the L2 norms. And so we have two different tuning parameters here. The lambda controls the overall level of the regularization, and then the alpha controls the balance between those norms. So the idea then here is to typically you cross-validate, over a grid, values for those. But in this visualization, we're going to actually just visualize how, the maps and the predicted values change based on those alpha and lambda. So I'll see if I can get to this. So you should be able to load this on your computer. And is it? Do I do Command plus maybe? Okay, so it's a little bit hacky. And so these things, we did some tricks. Actually, Nate knows a lot about how to do this. But so you have to so over the brain image viewer. That's actually, we got that from the Papaya viewer. So the problem was syncing these two pieces. So if you hover over the brain viewer and then use this kind of triangular bracket button that is also the period button, you can cycle through, and I'll just go to the top part of the brain where, okay, so we can see that things are appearing as we decrease the lambda parameter. And you can see over in this corner, the values of alpha and lambda. And so they also have all these. So, so we just have about 120 combinations of different tuning parameters there. And yeah, it's kind of got messed up there. But you just have to reload it sometimes, I guess. But anyways, that's something we could work on, and we'll discuss more later. But Nate will tell you how it works.
Now,
we got to be clear. When Joanna said we ran the ElasticNet, she ran the ElasticNet. There's no part of me in that there. So the hackery by which this works and doesn't require any kind of back-end server is that everything in this is pre-computed. So that yielded a new time series with one volume per every parameter set. And the voxel that I just saw are the weights of the predictions.
Okay.
Yeah, no, it's all good. Then what we do, we extracted the model per subject into a big spreadsheet where one row was a subject and one column was a set of parameter values. And then you can upload that to Scatterize, that what do you call it, thing?
Do you want to go to this? I don't
know.
No,
don't go to it.
Okay,
don't go
that
to
was something a project Nate did previously.
Yeah.
So that's how we made the scatter plot. Is like
yeah,
based on
it
that.
does some magic. And then we use that to actually feed the scatter plot on the web page, on the static web page. So it's a little cloud-based regression engine now, I guess, which is cute. And the synchronization is totally a hack. We just happen to scroll the two things at the same time, and it works-ish.
Right. So just some difficulties were the interfacing with the Scatterize, and we had to sort of change the keyboard shortcuts so they were the same button. And yeah, so syncing, interfacing with Scatterize actually required something I don't really understand.
Horrible hackery.
Anyways, so adding sliders for alpha and lambda would of course be, ideal, but that's another challenge. And it'd be great to make this easier to use with other data. So right now it's not straightforward. Okay.
And so the other angle you want to approach this from often is you do a univariate model fit at every voxel, and you want to know what that looks like everywhere. And you look at T-maps a lot, but it'd be neat if you could see the scatter plot at every voxel and maybe change your model around. And we got part of that to go. This one does need a server-side component. Make it a little bigger, a little smaller. And so here what you see is the correlation between that same connectivity map and the SRS total variable. And here you have T-map overlaid on everything, totally unthresholded. I mean, I guess, except it's thresholded a T of like 0.001 to get the total noise out. And as you click around or navigate around the brain, you can see the actual model fit at every voxel. So where it's bright colored, it's positive. Where it's green, it's negative.
And another thing is you can remove like sensor points.
You can't censor points in this.
Okay, you can't in this.
So the part of this that doesn't work is you can't rerun the voxel-wise model yet.
That's pre-computed.
Yeah, the voxel-wise model is pre-computed in this. We'll get there, but it's hard. So that's the demo part. How did you make it big again?
Shift F. Apple Shift F.
Well.
Command. Okay.
There were hard parts about that. For me, I was like, hey, okay, we're all done? Okay. Nope, it's all good.
That's basically it.
Slides real quick.
That's basically it.
That's basically it.
Yeah.
Okay.
Thank you.
Cool.
Okay, so we are the open science core team, and we started with a few projects that we wrote up that are already ongoing or old ones. So we had a lot of data to use, but actually we didn't use most of it. Our goal was to measure our open science across papers or across journals and show the trend, show that it's getting better, and maybe it doesn't mean good science, and present the O factor, a new measure, to replace the impact factor. So we started with thinking about which are the main components in the O factor, which components should we include. We came up with those four: sharing data, sharing code, peer participation, and policies regarding open access, citing preprints, things like this. Then we decided it would be too much to do the policies part, but it's mostly manually. So we made a new issue and didn't touch it, pretty much. Then we needed to decide on keywords. What are we going to look for inside papers in order to know that they share data code or whatever. So we talked about it a lot, used the whiteboard, and did a lot of Excel sheets. Then we scraped a lot of papers. So we needed to write Python code based on something that Scott did before.
decide which API to use. We used PubMed's one, and we took only full papers because at the beginning we had also only abstracts, which was kind of confusing. We used the cloud. It was hard, but Ariel helped us. And then we got this table with many, many papers, and for each one we know whether they share code, whether code is relevant, whether they share data, whether they pre-registered, based on our keywords. We did a lot of hacking. And then we analyzed the data. Before I'm showing you any plot, we want to be completely open about this is only open access papers, only PubMed API. It includes reviews and stuff that are not relevant for data sharing. And keywords should be improved, and it's very preliminary, so don't take anything too seriously. We can see that the trends are getting better, so sharing data, those are 10 different journals that we chose because we had enough data from and we know about them, pretty much. So you can see that the trends are getting better, so sharing data increased over time. Also code sharing, even more. It looks good, but still, if we look on the percentage of sharing data and codes from 2016, you can see still most papers don't do this. Pre-registration is not even shown because there was like almost nothing, okay? Almost nothing pre-registration. We computed an O factor. We tried to do it as similar as possible to the impact factor, so after a lot of debate and rankings and thinking about it, we decided about doing number of shared items, sharing data, sharing code, pre-registration, divided by the number of shareable items, like the citable items of impact factors, across 2 years. Those values are from what we got, from the papers we got for the years 2016 and 2017, from 10 different journals, plus computational biology is good, nature is good, we didn't want them to be, but they are. This is a small plot from the impact factor. There's a small outlier here of natures. This is the impact factor on the y-axis and the O factor on the x-axis, and there is not, the correlation is not too good if you know the outlier, which is good because we didn't thought it should be. I thought it should be negative actually. Then we did the Breda.
I know. When you click on it, I'm a little bit nervous. Sometimes it doesn't work.
No, it does. It is working. I tried. Ah.
Oh, see.
Ah, okay. Sorry, I'm seeing it.
Okay, so another thing that we wanted to try to figure out is how to do some interactive visualizations, and it was hard. It really was, but if you click on, can you click on one of those things? See, it changes whenever you click on it, so it is interactive. That's all that's interactive. The stuff on the bottom, it's not. So this app is just a Flask backend, which is Python, really simple. If my person uses pretty nice. The front end is actually a template that I got on GitHub, Bootstrap, because I'm not very good at anything front end. Or no. But so I really wanted to try to use the D3 framework, like JavaScript charting library, but I was like, oh no, there's got to be something a little bit easier. So there's this thing called DC, which is built on top of D3, but uses this really cool thing called cross filter, so it helps you kind of iterate through data that has a lot of different dimensions. But the biggest problem that I ran into is that D3 is being kept up with really well, so there's like a ton of documentation, and there's been a lot of big changes in between their versions, but then DC and cross filter, not so much. So I had a really hard time with the colors. That's actually probably the hardest thing. There's this one change, so now you can't really specify any colors, and for a long time, well, not really long time, but just a couple hours, but I was like, why are my line graphs not working? But then I realized that in the CSS, they were all white. Like the lines were white. So they might actually would have worked, but I'd already scrapped that, so. Oh yeah, and just hosted on Heroku.
Okay, wait a minute. How do I get them to do that? No.
Working.
I see that.
this is a presentation.
Okay, so we need to make it work like for the web app to have the data we showed you before in the plots to make everything flow. And we need other APIs, more journals, take only relevant papers. There is a team in what is the name of it?
Neurometric.
Yeah, yeah, which are currently doing the Neurometric, which is pretty much the same but for scientists, which is pretty cool because they started one day after us and our GitHub was already in their links. And we hope that someday there will actually be an O factor and it will change the trends and the culture, and we will admire this and not impact factor. And this is the team, and thank you very much to everyone who helped us, Christy, Tal, Ariel, Anisha, and all the rest. And thank you.
So this was not sort of an official project of any kind, if there are official projects. I think I mentioned, I don't know, I guess somebody took the...
PC?
Oh, thanks. A couple of days ago, several of us decided that there really has to be a better JavaScript viewer for functional images, which is actually a thing that like comes up every 6 months, and people spend a while on it and decide this is a crazy thing to do, and so they don't do it, which is smart. But several of us thought we would give it a spin and try to build a better JavaScript viewer than what exists now. There are actually some fairly nice JavaScript viewers. They're just not necessarily easy to use. And so here's a viewer. I think it's pretty cool. So you have at least 4 views, and you have your volume, well, surface, I guess, rendering here. You've got like orth views. You can manipulate all kinds of controls. And you know, I didn't have much time to work on this because I was mostly helping other people. And I maybe had like 10 hours, and Anisha put in a few hours, and a few other people put in some help brainstorm. So you're of course looking at this and thinking, wow, this is amazing. They built this in like 10 hours basically. And you're right, it would be amazing, but it's not truly amazing because we didn't build this viewer. It's not our viewer. We had nothing to do with this viewer actually. This is AMI, which is the thing we were planning to build a viewer on top of to make it easy to construct viewers. So Anisha spent like 2 hours building a shell for an app in JavaScript so that I could actually start developing, because in the like 5 years since I wrote any JavaScript turned into a whole different language, which I have to learn. And so I then spent some time trying to figure out how to get something to run within that shell of an app that Anisha had made for me. And that took about 6 hours. And finally I gave up and realized I wasn't going to actually understand JavaScript, so I just found some other starter thing on the web. And so a couple hours later this morning, here's the viewer. It's static, it doesn't, oh no, you can actually move, that's amazing. That's great, I didn't even realize I could do this. You can't zoom in or out, it's a little squashed because it took me about 2 hours to figure out how to change the dimensions and all. So, but that's a viewer, and eventually this will hopefully be a viewer other people can use. So anyway, the reason I mention this is because some of you probably are still having some imposter syndrome. You might be looking at some of these projects thinking, wow, that's amazing, but I can't do that, and we were like 8 people in our group. Never fear. I've been programming for a long time. I think of myself as a fairly competent programmer most of the time. But there were times yesterday and this morning when I was like, this is, clearly I'm an idiot. I don't understand JavaScript and I never will. I should just give up and pack it up and just go back to Python. So moral of the story is if you still feel like you don't belong here or you shouldn't be a developer, don't worry. You will always feel like an idiot as long as you program. But the hope is that in the interim you can actually create some cool stuff and other people use it. So hopefully you all appreciate that even if it doesn't feel like that right now. So I'll stop there. Thank you.
Let me get out of this. So I also feel like an idiot working with JavaScript and never use it.
You want to have a beer later or something?
What's that?
You want to have a drink later we can talk about it?
Yeah. So let me go to the presentation. So I started on the first day after coming up with, listening to everyone's ideas and thinking of my own. Here's this kind of diagram I thought that I'd like to do eventually, which is writing some add-on to PyBids to make it more easy to work with S3, then harvesting metadata, and then putting that in some sort of web page that's easy to manipulate, then get some other stuff that is in bids, like derivatives, like QC score and stuff like that, then think of a awesome name, and then have some sweet data visualization app. But in reality, that didn't happen. So I did come up with a name for the project called Metamorphometry. Eventually, it might become something, but I made this logo first because that's most important. I did do a pull request into PyBids, but it was basically just renaming something and copying things from one file to another. I started messing around with kind of working with S3, so I kind of have an idea on how I can do the things I want in within Python to access S3, but haven't really done anything to incorporate that into PyBids, but I'm hoping to work on that in the future because it'd be useful for me in my regular life. And then more importantly, I made this sweet pizza bar app, which the goal was to be able to vote on your favorite pizza and then have a bar chart and see like how many people like what pizza. And you can go to this website if you want. It's live now, pizzabar.firebaseapp.com. And if we go there, you see it has a great design template because Anisha didn't teach us about how to add Bootstrap JS to our stuff yet. But it does have an image of pizza, and it's from the public domain. And as you can see, someone really likes Hawaiian pizza. No. Also mayonnaise, cheese. Lint hasn't been a popular category. We can see some pepperoni and thumbs as well. And if you wanted to click, you can vote. And you can put in a new flavor like olive. Oops. And then, oh, cuttlefish is good. So one thing I didn't realize that took a while for me to actually do is if it's already in there, like how do you tell if it's already in there or not? So hopefully this all works. So now if I typed in cuttlefish, it should say, oh no, I broke. Well, I guess not. Before this morning or yesterday, it would say it's already in there and just add one to the vote. But it's cool with Firebase. You get this kind of database that it's owned by Google, and you can kind of sign up and like set up a demo app. And you can, when people click, if someone votes for cuttlefish right now, anyone, you can see that it goes up right away, and it's kind of like real-time database. And yeah, it took me a while to even do this simple thing, and it eventually kind of works, but not really. So that's all, and I'm hoping to actually use this to be kind of baseline of learning more about JavaScript and actually doing what I meant to do at the beginning. Okay.
So I know I was already up here with the MNI Atlas Reader, and about 24 to 36 hours ago, Dan seems to have that in the bag, and so I decided to indulge my desire for doing random things and tried this little project which Dan came up with the name for HackTrack, which was a little bit of a meta project for tracking hackathons. And so this was really inspired actually by the Docathon that the Berkeley Institute for Data Science hosted last year, where they had a running total of commits and documentation made for projects as the event went on. And so I thought that it would be really cool to do that for this event. I feel a little bit bad about it because all of the presentations have been super amazing, and it's like, we learned how to do AWS, and we learned how to do all of these things, and this is like a disgusting oversimplification of what happens at a hackathon. Hackathons are not about commits or issues or any of those sorts of things. It's about like skills acquired, connections made, things like that. Nevertheless, I decided to go ahead with it just because I wanted something to do. And again, Dan had MNI Atlas Reader in the back. So I am going to attempt to do this. I made a little binder instance, which was my first time making a binder instance, and it was super smooth. Really recommend. So let's see if we can do this. So yeah, so we can import HackTrack plotting as plot hacks, and we can come up with the date that the hackathon started,
go through and we can get all of our project info. So I don't know if many of you remember at the pizza yesterday, I was going around asking like if you were working on a GitHub repo, what was the username in the repository. So I put that all in a little CSV file with the user in the repository, and I shipped it with this as HackTrack.project list. But you could come up with your own project list for other hackathons. And then we load that and it gets a bunch of things. I've already done like scraped GitHub. So this is just loading pre-existing data. So if you open the binder instance, this will just load up the data since the last time I scraped, which was like earlier this morning. So if you made some last minute Git commits, this is non-representative. But then we can go through and we get a lot of information. GitHub provides a bunch of stuff about commits, authors, users, kind of all that good stuff. We can get some information about issues, when they were created, when they were closed, if they were closed, who commented on them. And so we got information for commits for 19 projects, which I think is how many projects there were, maybe. And then issues from 13 projects. The 6 missing projects there are just because no issues were created, which is fine. Making it pretty. These are some very, very basic plots. Again, we just started this yesterday, so we can just do something like total commits over time for all of the different projects. And looking at over the course of the hackathon, here's all the commits that were made on this GitHub repository. And again, you can see that some of these are low. That's not because nothing was happening. That's just because it wasn't on GitHub. There were other things that were occurring. We can also do commits by user. So actually, there are some people in here who are not here. So like Shotgunacine, that's because I scraped the PyBids repo, and so there are other people contributing, which is nice. It's not just us. And then we can do, for different projects, kind of cumulative commits over time. So you can list as many or as few projects as you want. Let me see if this will work. If I try and just get rid of this, it will attempt to plot all of them, which is wildly uninterpretable, but you know. We can do, Michael recommended coming up with a little scatter plot to look at lines of code added and lines of code deleted for each commit. Unfortunately, this needed to be put on a logarithmic scale because there were a few commits, especially from OFactor, where there were like over 600,000 lines of code added when you dropped those CSV files in. So we kind of like had to shrink that down a bit. And then, kind of, in my mind, a little bit more cool, we can look at issues. And so this is just a quick little plot of the number of issues created, and then the blue line is kind of how many of those have been closed. And so this is all during the hackathon over the past 4 days. And then we can look over time as well. So this one isn't cumulative. This is at any given point. We can kind of shift the frequency, how we want to chunk these issues up. So every 12 hours it would chunk, say how many issues were created, how many issues were closed for a given project. You can, again, list as many or as few projects as you want. And there are a few other little things that you can do with this, but this is all I was able to get. So again, it's a binder instance. You can load this up, although I think if we all tried to do it right now, binder would yell at me, so please don't, maybe. But like over the course of the next few days, if you're interested in looking back, you can, and you can load it up and play around with the data. And if you come up with any pretty plots that you think might be cool, we can try and add those into the actual main system. And then there's like a lot of other work that could be done. Looking at pull requests, looking at comments on those sorts of things. But this was really just kind of like a little fun time project to say, everyone did a great job. So thanks.